Hello everyone, hope you are enjoying the lectures of fundamentals of combustion for propulsion. There were some requests for a problem solving session. I have put together some material I have put together a few simple problems that will reinforce some of the ideas that we have discussed so far in the course. Uh, so in this short video, we'll go through uh, a few worked examples and see how it goes from there. Okay, I'll start with the idea of, we'll start with the, so this is okay, let's start with the idea of stoichiometry. Let's take for simplicity the fuel as normal octane and the oxidizer as air. Remember that air has approximately 21% by volume of oxygen and 79% by volume of nitrogen. Okay, this 3.76 is nothing but, maybe I'll explicitly write it as 79 by 21. Okay, for every 21% of oxygen there is 79% of nitrogen. This is what we'll treat approximately as air. There are some traces of argon, carbon dioxide and so on, which we will ignore for the purposes of the current discussion. A stoichiometrically balanced reaction for octane should result in 8 moles of carbon dioxide and 9 moles of water vapor or water plus whatever nitrogen is left. Okay, to balance this reaction we need 8 moles of diatomic oxygen and 4.5 moles of diatomic oxygen for the steam part. So the total number of diatomic oxygen moles that will balance this equation is 12.5. So 12.5 is 12.5 moles of oxygen is required for stoichiometrically balanced reaction of octane, and since 21% of oxygen comes with 79% of nitrogen in air, we also have that 79 by 21 times 12.5. Okay, so this is a stoichiometrically balanced reaction for octane. With this, now we can calculate the oxidizer to fuel ratio. The oxidizer here being air, this is also the air to fuel ratio for stoichiometry. Will be the amount of, this is on mass basis, this is just the amount of oxidizer, which in this case is 12.5 times the molecular weight of oxygen, which is 32, plus 79 by 21 times the molecular weight of nitrogen. This is the mass of the oxidizer divided by the mass of the fuel. The fuel has 8 carbon atoms, each 12 grams per mole, plus 18 hydrogen atoms, which is 1 gram per mole. Okay, so this will give you an air to fuel ratio of about 15.1, which is a number that is more or less for all hydrocarbon fuels. The oxidizer to fuel ratio or the air to fuel, stoichiometric air to fuel ratio will be about 15 to 20. So that is as far as stoichiometry is concerned. Let's move on to the idea of formation enthalpy. This is also something that we discussed in class, and I'll take the same example to motivate the idea of formation enthalpy. gives recall that formation enthalpy is defined as the enthalpy of a reaction in which a component is formed from its naturally from the component elements which are occurring in the elemental natural form. Let me repeat that. Okay, let me first give this elements in naturally occurring form are taken to have zero formation enthalpy. Okay. Others which are not naturally occurring form from these elements, okay, and the enthalpy of that reaction is called the enthalpy of formation. I will give you a simple example. Let us take for example octane itself. Octane is made up of elemental carbon in graphite form, which is a naturally occurring form, plus 9H2, which is the naturally occurring form of hydrogen element, which is diatomic hydrogen gas, will form C8H18, which is a liquid under normal conditions of temperature and pressure, and the enthalpy change of this reaction is the enthalpy of formation of octane, which as it turns out to be is negative 250 kilojoules per mole. Okay. Turns out to be negative 250 kilojoules per mole. Let us call this reaction 1. Let us call this reaction just reaction R. And if you take CO2, to form CO2, carbon and oxygen, by the way the naturally occurring form of oxygen is gaseous oxygen in diatomic form, forms carbon dioxide, gaseous form. The enthalpy of this reaction is the formation enthalpy of carbon dioxide. Okay. And the other one that we will need for this discussion is the formation reaction for water. Gaseous hydrogen combines with gaseous oxygen to form liquid water, and the formation reaction, this is a formation reaction for liquid water, and this has an enthalpy of negative 285.8 kilojoules per mole. Keep this other reaction also in mind. It's a reaction for steam formation, which is same H2O but in gaseous form. The enthalpy of formation of this reaction, where the final product, which is water, is in steam form, is negative 241.8 kilojoules per mole. Okay. Now if you observe, we can write reaction R, as equal to 8 times reaction 2 plus 9 times reaction 3 minus reaction 1. Okay. Excuse me. Notice that in reaction R, 12.5 times 79 by 21 nitrogen is on both the sides, therefore for the purposes of stoichiometry, for the purposes of enthalpy calculation, it is the effects will cancel out, so it need not be explicitly included. Therefore, the enthalpy change or the enthalpy of combustion of octane, which is the enthalpy change of reaction R when octane plus stoichiometric amount of air gets converted into carbon dioxide and water vapor, carbon dioxide and water, and the reactants and the products are at the same temperature and pressure. That is, you have burnt octane and air, it has gone to a higher temperature, you have extracted all the heat from the product gases and brought the product gases back to 300 kelvins. That amount of heat is the enthalpy of combustion of octane, which from the definition of formation enthalpy now is 8 times the formation enthalpy of CO2 plus 9 times the formation enthalpy of H2O liquid minus the formation enthalpy of octane, sorry, C8 H18 liquid. Okay. You can plug in the numbers. I have given you the formation enthalpies earlier, and then you will get what is called the higher calorific value of octane as negative 5470 kilojoules per mole, which when divided by the molecular weight of octane will give you the calorific value. Okay, sorry, this is per gram. I have explicitly retained the negative sign because this is an exothermic reaction. Okay, and it is HCV when the final product, the final water is in liquid form. But in reality, the combustion products are usually at a temperature that is much higher than the boiling point of water, and water usually exists as steam in real applications. Under such conditions, the heat or the energy that can be extracted by combustion of this fuel when the water is in water vapor form is you should use the formation enthalpy for steam instead of liquid water. If you plug in that number in the equation that I showed in the previous page, you will get 5074, slightly lower energy, because the energy that is required for converting liquid water into steam has been taken from the fuel itself. This will give you negative 44.5 kilojoules per gram. This is the lower calorific value and the relevant number for the enthalpy of combustion of octane, and this is another feature of all hydrocarbon fuels. On a mass basis, more or less all the hydrocarbons have the same calorific value of about between 45 and 50 kilojoules per gram. So with this background, let's move on to the third idea, which is the idea of adiabatic flame temperature. The idea of adiabatic flame temperature, and let's take the same reaction and calculate the adiabatic flame temperature of the products. We will assume as a first approximation that the products are only carbon dioxide, water vapor and nitrogen. Okay. Now it is very easy to calculate the adiabatic flame temperature. We saw just a few moments ago that the enthalpy of combustion, the lower calorific value of octane is 5074 kilojoules per mole, that is exothermic, and when you burn octane, what happens is that this 50 for every mole of octane that you burn, 5074 kilojoules of energy is of chemical energy is converted into heat, and that heat is used to raise the temperature of the product gases from rise the temperature of the product gases. So if we start with an initial temperature of 300 kelvins, and supply 5047 kilojoules of heat to these product gases, whatever temperature the product gases go to is the adiabatic flame temperature. Therefore, the adiabatic flame temperature can be simply calculated by saying that by burning 1 mole of C8H18, 5047 kilojoules of energy is liberated, and that simply raises the temperature of 8 moles of CO2, 9 moles of H2O, okay, plus 12.5 times 79 by 21 moles of nitrogen, okay, times Tf minus Tc. Okay. So this simple formula, we know the molar specific heats of nitrogen, water vapor and carbon dioxide. It is of course Cp is Cp for multi-atomic molecules are a function of temperature, but approximate values for these quantities are 42 joules per mole Kelvin for CO2, 32.4 joules per mole Kelvin for water vapor, and for nitrogen it is 39 joules per mole Kelvin. Okay. So if you plug in these numbers, you can get a value for Tf, which is T0, which is the initial temperature is 300 kelvins, plus 5047 divided by, well, I didn't calculate that number, 8 times 42, excuse me, 9 times 32.4 plus 12.5 times 79 by 21 times 39, okay, we'll get a number of 2351 kelvins. So an adiabatic combustion at constant pressure of octane with stoichiometric amount of oxidizer, which is stoichiometric amount of air, producing only 8 moles of CO2, 9 moles of water vapor and rest nitrogen. Assuming these specific heat values, the adiabatic flame temperature is 2351 kelvins. This is a simple estimate for the adiabatic flame temperature of octane. Okay. Remember this value. Tf is 2351. Assumptions are CO2, H2O and N2 are the only products. And Cp bar assumed constant. Now, I gave a demonstration of how to calculate the adiabatic flame temperature using the chemical equilibrium and analysis code, and if you use that code and calculate from CEA, if you calculate, you will get an adiabatic flame temperature of 2274 kelvins for the same reaction, octane with stoichiometric amount of air. Why is there a difference? There is a difference of about 80 kelvins. Okay. Why is there a difference? So if you look at the product concentrations that CEA gives, product concentrations that CEA gives, in addition to CO2, H2O and nitrogen, you will also find CO, H2 and traces of several other species. Okay. So one of the reasons, or one of the primary reasons why the estimate of the adiabatic temperature from the simple calculation differs from the actual numbers is because of the phenomenon of dissociation. What I mean by that is that CO2 at 2351 kelvins will not remain CO2, it will dissociate into CO and O2. Similarly, water vapor at 2351 kelvins will not remain as water vapor, but it can dissociate into hydrogen and oxygen, and several other reactions can happen of decreasing importance. And these dissociation reactions are endothermic, and therefore they take up heat and bring down the flame temperature. Okay. And the way NASA CEA calculates the equilibrium temperature is by minimization of Gibbs free energy. The standard thermodynamic procedure for calculating equilibrium states, minimization of Gibbs free energy. I will not go into the details, but I leave it as an exercise for you to try and calculate the equilibrium composition. Assume that you have pure CO2 at 2351 kelvins or some high temperature 2000 kelvins, and if the temperature is held constant at 2000 kelvins and the pressure is held constant at 1 bar, and you can consider a few cases 1 bar, 10 bar and 30 bar, try and calculate the equilibrium composition of CO2 dissociation. That is, if you allow for sufficiently large time, at the end of it, how much of the CO2 would have dissociated into CO and half O2. Okay. As a simple example of that, you can look at the problem, for example, of dissociation of pure carbon dioxide into carbon monoxide and oxygen. You can calculate the equilibrium composition by the simple relation which connects the equilibrium constant to the Gibbs free energy change of this reaction, which is exponential minus delta G 0 by RT. Okay, this is the Gibbs free energy change for this reaction. This is one equation. You have three unknowns. The two other equations come, this is one equation. The other equation is conservation of number of atoms called atomic balance. If you start with 1 mole of CO2, then at the end of the process, once equilibrium state is reached, you will still have an Avogadro number of carbon atoms and twice the Avogadro number of oxygen atoms. So that is atomic balance. That will give you one additional equation to solve. The third equation is a simple relation that the sum of the mole fractions must be equal to 1. Okay. If you put these three equations together, you can solve for the equilibrium composition of CO2 dissociation, steam dissociation, water gas shift reaction and so on and so forth, and combine this with the calculation of the adiabatic flame temperature. You will get from starting estimate of 2351, you account for more and more dissociation, you will slowly approach the number that you get from CEA. In fact, CEA is essentially does the same thing by minimizing the Gibbs free energy, and you can use that tool to calculate. One advantage of doing this calculation is you can check the effect of initial temperature. We know that as the temperature becomes higher and higher, the extent of dissociation goes up. You can see the effect of temperature. I will not say initial temperature, I will just say temperature. And you can also see the effect of pressure. At a given temperature, as the pressure increases, you will see that the extent of dissociation decreases. Okay. The famous Le Chatelier's principle. Okay. Fine. That brings us to the end of the discussion on adiabatic flame temperature.